Welcome back, class. In this video, I want to talk about, I want to conclude our section on buffers and talk a little bit about two kinds of ways that we can think about how effective a buffer will be. And that is its buffer range and its buffer capacity. So let's talk about generally what we mean by those, and then we'll go through and talk about in more detail. So to have an effective buffer, you want to be able to neutralize, quote, moderate amounts of both added acid and base. Now, of course, with any buffering system, there's a limit to how much of these acid and base you can add before the pH changes significantly, right? At some point, you're going to react away all of what that component of the buffer, which is reacting, right? So there is always a limit. Now, the buffering capacity, right, is essentially the measure of this actual limit, right? So the buffer capacity is the amount of acid or base a buffer can neutralize. And as we'll see, that will essentially depend on the absolute concentrations of our weak acid and our conjugate base. Now, there is also what's called the buffer range. And that is the pH range in which a buffer can effectively hold the pH, right? So it's the pH range in which the buffer can be effective. Now, the effectiveness of a buffer depends on two factors, right? We already talked about the second factor here. That's the absolute concentration of our buffer, our acid and base. The other one is the relative concentration of the buffer acid and base. So meaning, do we have equal amounts? Do we have more of the acid than the base part of the buffer? That's what we mean by the relative amounts. So let's look at what those things do. So we're going to talk about capacity first here, because it's probably the most straightforward. So again, the buffer capacity is the amount of acid or base that can be added to a buffer without seeing a large change in its pH. And not surprising, the capacity increases with increasing absolute concentrations. So the idea is if I have 0.1 molar of my weak acid, I have a certain capacity. If I have 0.2 molar, I'm going to have a higher capacity, right? So the more moles, or the higher concentration of our acid and base component, the larger the capacity is. So we can look at it generally here as a more concentrated buffer can neutralize more added acid or base than a less concentrated or dilute buffer. Okay? So that's essentially buffer capacity. Now, if we talk about the relative concentration, now the first thing to note is a buffer is most effective if the ratio is 1:1. And so we're going to use this idea a lot of the acid to base ratio. Right? And so if we're talking about the two components of our buffer system, if there's a 1:1 ratio that they're equal, then this will give us the, quote, most effective buffer. Now, it is not always possible or even what we want to have a 1:1 concentration. There are perfectly valid reasons why you might have more one than the other. And so with keeping that in mind, a buffer can be effective with a acid to base or base to acid, however you want to think about it, ratio of between 0.1 and 10. So essentially what that means is we can have up to 10 times as much acid as base or 10 times as much base as acid. That's all that means. Now, another way of thinking about that is this allows a pKa plus or minus 1. Right? That's sort of what is setting this limit. And we'll talk more about that maybe as we go through this. Now, as this ratio approaches 1, the ability of a buffer to neutralize both types of impurities, acid and base, gets better, obviously, right? Because we have, more of them, of one or the other, right? If it's shifted one way, then it has a better ability to neutralize one, but not the other. And so if we have a buffer that we know is going to be exposed to mostly acid impurities, then it would make sense to maybe shift it to have a ratio that has more base than acid. So maybe you, instead of having a 1-to-1, have a 2-to-1 or a 3-to-1, right? And again, the same thing, if we know we're going to have to generally deal with basic impurities, it would make sense to not have a 1-to-1, but have a ratio that leans toward having more acid than base. Now, just as we saw with capacity, the buffer effectiveness will generally get better as we increase the absolute concentrations as well. So the buffer becomes even more effective when the acid and base concentrations are larger. Right? You know, this is just a numbers game, because that means any shift in concentration is going to be less significant if we have a large initial concentration. So the best buffers are going to have higher absolute concentrations and a ratio close to 1-to-1, right? If you just sort of want to say, oh, this is the most effective buffer in all situations that I can have. So let's talk about this idea of range, right? What do we mean by the range of a buffer? Well, we've stated that this range that the range in concentrations can either, we could have, you know, let's say we just have, if we draw it from, you know, let's say I have acid to base, I could have a 10-to-1 concentration all the way to a 1-to-10 ratio. So these are, you know, this is what I'm talking about here as, you know, this is sort of the effective range that I can create buffers within. Now, if we use the Henderson-Hasselbalch to sort of mimic these numbers and what it might look like, if I plug in, you know, the lowest ratio. So remember, the Henderson-Hasselbalch equation uses the ratio of the base to the acid. So in this case, if I have 10 times as much acid, right? So if this ratio is 1-to-10, then I get this kind of scenario, right? And I get a pH that is equal to pKa of my acid minus 1. If I use the other extreme and I have a ratio of 10 times as much base as acid, so if I have 10 times as much as my base as I have my acid, that gives me this expression, and I get the pH equals the pKa of the acid plus 1. So this is the idea that the effective pH range that can be maintained is the pKa of the acid. So this is the pKa of the weak acid of our buffer plus or minus 1, right? So if that weak acid has a pKa of 3, well then the effective buffering range is going to be between 2 and 4. Right? That's the idea. And so when choosing an acid system to create our buffer, we would want to choose one that has a pKa closest to the pH, right, that we need to maintain with the buffer. Right? Okay, so I think I've talked about these, so I'm not going to get into this too much. I think this is a little repetitive. So this is the idea of buffer effectiveness, buffer capacity that we want to talk about. So just to kind of summarize, the most effective buffer is going to have larger absolute concentrations and a 1-to-1 ratio. But buffers in general can be effective anywhere between a 10-to-1 acid to base ratio as a 1-to-10 acid to base ratio. And there's valid reasons why you might choose to shift the ratio based on the type of impurities that you might experience. And when choosing a buffering system, you want to you want to say, I want to maintain a pH of this of 5, right? Then you want to choose something, an acid that has a pKa close to 5, right? Because that buffer can maintain a pH plus or minus 1 of the pKa of the acid. So a little bit about buffer effectiveness, looking at both the buffering capacity and the buffering range.